Let's do practice problem number 15. It's on page 265. And here's what we've got. I'll read the problem. It says bullets bounce from Superman's chest. Suppose that Superman, with a mass of 104 kilograms, while not moving, is struck by a 4.2 gram bullet moving with a speed of 835 meters per second. The bullet drops straight down with no horizontal velocity. How fast was Superman moving after the collision if his super feet are frictionless? So there's the super feet, and they have no mu. Okay. So let's, now I'm going to add this to the problem. I want to know what is the change in kinetic energy of this system. And so let's solve. Now, this is an inelastic collision. And in an inelastic collision, you always start with momentum. The initial momentum of my system equals the final momentum of my system. Now I look at this system before the collision. Superman is not moving. Superman has no momentum. All the momentum is in the bullet. So I'll just say M1, V1 initial. 1 is the bullet. 2 is Superman. Now, after the collision, it said that the bullet just drops straight down and has no horizontal velocity. So just after the collision, the bullet has no velocity. So all of the velocity had to be transferred into Superman. So, I mean, all the momentum is now with Superman. And this is it. This is the initial momentum of my system. This is the final momentum of the system. This just before, this just after the collision of the bullet with Superman's chest. So, now we can solve for our unknown. V final 2. Sometimes I get the subscript screwed up. Sorry about that. So this is going to be M1, V1 initial, divided by M2. Okay, the mass of Superman. And so M1 is very tiny. But V1 initial is very large. And the mass of Superman is fairly big. And now I get a calculator. Well, look at the dimensions. Yeah, the units cancel out to get meters per second. So V final for Superman, final velocity of Superman is 0.0042. It's this one, times 835, divided by 104. Now, very slow. I got 0.0337. We'll keep 3 significant figures. That's 3 centimeters a second. Right? Move it over. That's slow. But Superman is big, and the bullet was tiny, and even though it was going really fast, you know, Superman's not going to it's not going to be moving. It's not going to be moved by that bullet very much. Okay, and that's my answer. And let me check, make sure I did it right. Point. Oh yeah, this is the book is wrong. I got to really make sure. Did some of you others do this problem and get that answer? Yeah. Okay. Yeah, the book's answer is wrong in the back. So I'm going to go with this. Now, how much kinetic energy is lost? Delta K. Well, what is that? Delta K is equal to K final minus K initial. Well, that's 1/2 M. Well, where is all the kinetic energy at the end? It's all in Superman, because the bullet stopped moving. So M2 V2 final squared minus the initial kinetic energy. Where is all the kinetic energy beginning? It's all in the bullet. And it's initial squared. V1 initial squared. Well, if I plug my values in, 1/2 m2. Superman weighs, or has a mass of 104 kilogram. But look at this tiny velocity. And this tiny velocity gets squared. When you square something tiny, you get something even tinier. Minus 1/2, well, the bullet is pretty tiny. But let's look at this velocity. This initial velocity is huge. Now I got to get these to see 0.5 times 104 times 0.0337 squared equals, oh my goodness, 0.059 joules. Almost nothing. Minus the initial kinetic energy, 0.5 times 0.0042 times 835. Oops, let me move this so you can see it. 835 squared equals, oh my goodness, 1,464 joules. Well, this minus this is lost. This is insignificant compared to the significant figures here. So you can essentially say it lost all its kinetic energy. Where did it go? Heated up Superman, heated up the bullet. It all became thermal energy into the environment. So, negative 1,464 joules. All is lost. Well, almost all the kinetic energy was lost. Anyway, here's the whole problem. Let me zoom out. Hope you enjoyed this Superman episode. That is all.